Good morning. Thank you for I'd like to thank the organization for the occasion to be here and speak about our work. And actually, my presentation regards our latest achievements in recycle and recovery of end of waste polyolefins. But as I was organizing my information for the presentation, I thought I would like to give you a more general overlook on more successful cases we've been working on regarding circular economy and recovery recycle of waste in general. So we will start with the asphalt case, and we will see also some other projects we've been working on. So I'll try to share my screen with you. Okay, so just tell me if you can see the presentation, please.
Yes, we can see. Yes, we can.
Okay, very good. So eco-friendly end-of-life disposal by with a circular economy approach. So that's the general idea. Just a few words to give you a brief introduction of who we are and what we do. I work for the University of Venice Foscari at the Department of Molecular Sciences and Nanosystems, and I founded a spin-off called Crossing. It's an SME now, innovative SME, and we are involved with innovation and sustainability in processes. We work generally with the development of new products or processes. We've been working with the leather industry, biomass recovery, plastic recycling, paint and coatings, packaging, textile, food and animal feedstocks, pharmaceuticals. So you see, it's quite a vast area of application and interest. Specifically, we also have some technologies which have been patented by the company regarding a specific class of chemical compounds, which we call ACL for cross-linking activators. And they are we use them to modify, stabilize, and give specific additional characteristics to the products you've seen in the previous slide. So it's used for tanning leather, modifying giving antimicrobial properties to paints, textiles, surfaces, and so on, coatings, and so forth. In this connection, we've always been very interested in developing our technologies towards sustainability, environmental, sustainable and economically sustainable processes within the principle of circular economies. And for this reason, we've been working with funded projects, European and national funded projects on different thematics, which I will show you now, starting from the asphalt. But just to give you a general outline of the panorama in which we are oriented, I think it should be useful to take into consideration a couple of data. Europe inhabitants have something like 5 tons per head. And so that means that each of us, in an average which of course takes into consideration also the industrial part of industrial waste, has a production yearly of 5 tons. So that is a huge amount. And these are Eurostat data of 2016, but they're almost roughly the same now. Of these 5 tons, around 45–46% is disposed in waste disposal plants. 37–38% is recycled, but unfortunately, and still now, around 17–70% of this waste is sent to incinerators. So this means we are producing a lot of CO2. Well, here you see also the distribution of the different impacts of the various manufacturing and construction sectors on the distribution of the waste in a percentage. And you see how constructions and mining, in fact, are the most heavy impact processes on as far as waste production is concerned. And here again, another data which regards how much kilos per inhabitant we produce in Europe by country. So I think this is an interesting data. You can find this is quite a recent data. You can also find more updated probably data now in Eurostat website. And Italy, for example, produces 2,617 kilos of waste per inhabitant, while other less industrialized areas, geographical areas, produce more. So there's still a lot to do in terms of recovery and reuse and valorization of waste, and also the possibility to this is I think it's a possibility. It's a way by which people, European countries who develop new technologies should transfer within the logic of the European Commission technologies which are developed in a certain country to other countries in order to increase the number of people that can benefit from a specific technology that is devised in a specific European country. So coming back to circular economy is a drastic change of paradigm. We are not going in a line. We're not producing, using, throwing away, but we are producing, using, and recycling. So it's an eco-design which starts ab initio, and it is now something which is consolidated and should be one of the best practice adopted by companies and producers and also researchers to develop new technologies and rethink old technologies. So this you know also, I will skip it and we'll go straight to the specific applications. So this is the first project I want to talk to you about. It's a European funded regional project. We are working with recovery and recycle of polyolefin waste. We've heard this before today, but we're using it for a different application. We're making road pavement, so asphalt. Asphalt is, well, first of all, what is the impact, generically speaking, of a technology that is able to recover and recycle polyolefins or plastic in general? For 1 ton of plastics which are recovered today, over 400 tons are sent to the incinerators, and 1 ton of incinerated plastics produces 1 ton of CO2. So this gives you a weight of the impact, straightforward impact of this, of what plastic recovery and recycling means. Just to give you a general idea, because I mean it's difficult to understand what a ton of CO2 is. You could parametric with the production of a car, of CO2 produced by a car used yearly, which is around 5.3 metric tons per year. So this means that 5 tons of incinerated plastic produce as much as one car. Okay, how much plastic do we produce yearly? Do we recover yearly? In Italy, the data was in 2018, 1.2 million tons of plastic yearly. So if you can make the appropriate percentage and you calculate the amount of CO2, it makes a lot of cars. Well, what did we want to do? We wanted to produce high quality asphalt. Mainly, we wanted to reduce the amount of end of life polyolefin waste produced and reusing it. Okay. And by doing this, we realized that we could substitute additives, fossil-based additives, which are generally used for asphalt production, by using polyolefin waste. So we have a double advantage. We recycle something which would be burnt, and we avoid using fossil-based products, additives. So and then we are now in the way of evaluating the environmental and economical impact of the new technology by LCA, LCC. We will be doing a PEF evaluation as well for the environmental footprint of the technology. So we started from something really very dirty and unpleasant, which is this sinking fraction of polyolefins, which polyolefins are collected by a specific disposal plant. Then they are cut into small flakes altogether. It can be many different kinds of polyolefin and not polyolefin, also plastics. The polyolefin, the floating fraction is recovered to make secondary, primary materials for other plastic production, polyolefin production, while the waste left from this separation, which is the sinking part, contains everything. Plastics of any sort, steel, dirt, and so on. So what we did is wash further this what we call WOPO, waste of polyolefin, because it's what remains after you've taken the polyolefins out. And we've processed it further in order to be used as a substitution for the petrochemical polymers used in asphalt production. And in fact, we had very satisfying results. You see, the starting material we use is really heterogeneous in the most extensive way. We have everything in there. And it's also difficult to have a statistical average of what is in there. But as a matter of fact, it doesn't really matter. I mean, the asphalt is able to accept a highly heterogeneous plastic additive, and what we use about 0.25%. So the amount is very small, but it's comparable to the additives which they usually use. And we managed to have characteristics which were measured according to the normal standards used for asphalt production, comparable to high quality asphalt for highways, for example.
And also we've made some tests on small patches. It's about a few meters of asphalt in the place where they were producing the asphalt, and it's been tested for 6 months, and with trucks going over it and so on. So this is a real test of the efficiency. In about 15 days, we will be removing this asphalt. It's been there for 6 months, and we will be using it to recycle further to see the recycling for the asphalt as it's been removed and recycled. And we also made some economical evaluation, and it comes out that substituting the polymeric fossil-based products, which are generally used, we come out with CO2 credits, of course, and it's roughly an economical advantage of 490–500 euros per kilometer of this asphalt being used. So this means that we are having an advantage from an economical point of view, and we have the advantage of not having the incineration of roughly it's 4.5 kilos per kilometer, which means that for about 300–400 kilometers of asphalt, we would be fulfilling all the end of life. We would be using all the end of life plastic of the disposal plant we are working with presently, and we would be able to have even further advantages if we could pave, so to say, the pavement which is changing in Italy over the year. Other case studies are regarding also circular economy. This is a LIFE project. It's been funded by the European Commission, finished in 2019. And in this case, we were working with recovery and recycle of agricultural waste for the production of chemicals to be used in the leather industry. The leather industry, you see here, there's a very happy cow ending up in a series of sequences of steps. Of course, we have to remember that the leather industry is by nature a circular economy based process, since it reuses a waste from the food industry, and therefore we have a processing of a waste, of a byproduct, which is transformed into something which is a high value product. Here you see a nice bag, and they use a lot of chemicals. Some of them are highly hazardous, and this is why the leather industry has a high environmental impact, in fact, overall. And we've been taking byproducts deriving from beetroot, sugar cane, and also from the leather industry as well. And we've been transforming these in chemicals, which could be used as retanning and fattening agents for the leather industry. And in this case, this is a really the circular economy principle at its most virtuous top, I would say, because a waste from the leather industry was transformed by enzymatic and chemical transformation into a product to be used within the same manufacturing area. So this is one, and then we have other cases. For example, this is recovery recycle of agro-industrial waste for food packaging. There's a lot of work regarding carboxymethyl cellulose, which is this, and being used for film packaging. And we've devised a new technology which allowed us to cross-link further the with the use of our cross-linking chemicals to cross-link further the biopolymer in order to achieve films which were highly stable, although biodegradable in time. And we are now, and this is being published on carbohydrate polymers. And we've also now, we're working on a similar chemical stabilization of ketone waste. You know that ketone is one of the most abundant biopolymers in nature, as it is the comes out of the what do you call them, crabs and shellf, for example, and squid shellf, and they can be used again to make edible films. And in this case, ketone has also antimicrobial properties. So we cross-link these films and we use them to make packaging. And we also tested their antimicrobial activity, as you can see here, on Streptococcus aureus, Klebsiella pneumonia. And that's all. This is the group working on all these nice things. And I thank you for the attention. If you wish to find more information about us, you can visit our website, which is reported here. Thank you again. And if you have any questions, I will be pleased to answer.